Okay, thanks for having me today. I'm a research fellow here at DARE, and I'm mostly a domain scientist in climate science. And I've touched upon various mathematical methods that are quite new to the field in the past. And here at DARE, this is sort of my first foray into Bayesian methods. How do I advance these slides? Ah, there we go. So what I'm going to do today is tell you a bit about the phenomenon that I'm interested in, which is El Nino Southern Oscillations. That gives us both El Nino and La Nina events. And then I'll tell you a little bit about how we think about what is going to happen in the future in terms of climate change. I know many of us here have interests in climate adjacent fields, so hopefully that will be a useful introduction for many of you. And following that, I'll present a few quick early results from one of my projects. So El Nino Southern Oscillation is this phenomenon that gives us El Nino and La Nina events. The events occur every few years. El Nino is warm and La Nina is cold. So the picture on your right shows an El Nino event, which has warm anomalies along the equatorial Pacific. So you can see a sliver of North America, a little bit of Australia in the corner. That's the globe. And you can also see that there are winds blowing from west to east. La Nina looks sort of like the opposite of that, where you have cold anomalies at the surface on near that equatorial belt. The time series at the bottom shows years on the x-axis, so you can see how often El Nino and La Nina events occurred. And as you can see from the graph, there's sort of a characteristic time scale to that, but no real regularity. So being able to predict this is a challenge, and while we are able to do it a few months in advance, sort of giving us a better lead time is an ongoing effort. El Nino and La Nina events have effects all over the world on rainfall and temperature. This highlights some of the effects that occur just in December to February, but they can really occur at any time of the year. And this happens because El Nino and La Nina events shift the center of convective activity over the Pacific around. And that then perturbs the atmosphere, and those perturbations result in all these disturbances around the world. Australia is a particularly vulnerable country when it comes to this. This is a schematic from the Bureau of Meteorology, and it shows the changes to rainfall and temperature during an El Nino event. And you can see it's both drier and hotter during El Nino, and we get sort of the opposite, but not exactly during La Nina events. So to get a little bit into what physically is going on there, the normal state of the Pacific is like this. So this is a sort of cross section through the ocean in the Pacific. On your right, you can see sort of North America, South America, and on the left, a very distorted Australia. The colors at the surface represent warm and cold temperatures. So you can see the western part of the basin is typically very warm. The eastern part is typically very cool. And over that warm water, you have a lot of convective activity that's producing rainfall, but also changing the circulation of the atmosphere. Near the surface, the atmosphere has winds that are blowing from east to west. And what that results in is a pushing of the surface water away from the coast and away from the equator. And as a result, you get colder water from below that hasn't seen the sun coming up to the surface. And that gives you really cold temperatures near the surface of the ocean that you don't get in the tropics otherwise. Now, during an El Nino or La Nina, that sort of normal balance gets out of whack. And during an El Nino, the warm temperatures really spread across the whole basin. During a La Nina, you get the colder temperatures extending further into the west. At the core of how that happens is a feedback known as the Bjerknes feedback. So imagine that in your system, you have, for some reason, a small warm anomaly in the surface temperatures of the East Pacific. That then will weaken the gradient of temperatures across the Pacific. And as you probably know from looking at weather maps, changes in temperature will lead to changes in air pressure. And that then will change the winds that go across. So you end up weakening that gradient and weakening the winds. Weakening those winds will then reduce the amount of upwelling of cold water from below. And that will reinforce your warm anomaly. So you get this feedback from a small perturbation, and that gives you an El Nino event that can last several months and cause lots of trouble for lots of people. When the feedback proceeds in the opposite direction, that is, you get cold SSTs in the East Pacific, and you end up strengthening the gradient, strengthening the winds, upwelling more. That gives you a La Nina event, which produces the opposite effect. So the reason why I'm bringing up this feedback is that it's at the core of what really makes the system tricky. You can imagine trying to do causal inference from data on this is very tricky. If you wanted to build a graphical model, it's a cyclic graph, and a lot of our methods would break. So bringing machine learning and new statistical methods to this type of problem has been an ongoing challenge. And that's sort of where I'm hoping to break through a bit. The particular piece of this feedback that I'm going to focus on in my project is the east minus west gradient of temperature, because it's been observed that that gradient is changing with climate change. So to quickly go over how we know about climate change and what we use to make those projections of, we should keep temperatures from rising more than 1.5 degrees C, where those sorts of numbers come from. We use something called the general circulation model, also just broadly known as an Earth system model or a climate model. So what it is a numerical simulation of fluid flow in two layers. So there's the ocean and there's the atmosphere. And those are resolved at a number of levels in depth and height. And you have a latitude, longitude grid. So this is a discretized fluid dynamical simulation. And within those fluids, you have tracers that are changing the properties of the fluids. So there's water vapor, which is very tricky because it does things like evaporate and condense and change the density of the air it's in. There's also salt in the ocean and a number of other chemical tracers. You have to also account for the fact that the sunlight coming into the Earth is changing over the course of the seasons. The area of maximum energy input is changing. And the irregularly shaped continents on the Earth mean that you cannot do this analytically. You have to do it numerically. Like all the shapes of the continents, the mountain ranges, all that needs to be put in somehow, and you can't, reduce it to a nice clean box or something. So we use a set of pretty fundamental equations that we're solving on that grid. At the core of every climate model is this set of 5 equations. And you don't really have to pay attention to the equations themselves, but just what's on the left, which is that they are conservation laws for the most part. So they're conservation of mass, conservation of momentum, also known as Navier-Stokes, conservation of energy, tracers, and hydrostatic balance. So that's to do with gravity. And it's these fundamental equations that are being put on that spherical grid and being solved over time steps. Now, there are some of the terms in these equations that you can't perfectly resolve. So you can imagine that if you have a latitude longitude grid, one degree longitude is about 100 kilometers wide. So you're not going to resolve things like the processes inside a cloud or a turbulent eddy in the ocean. So you need to make choices about how to represent those statistically to put them into these equations. And people spend their whole careers developing smart ways to do this. It's a very difficult problem, and that's somewhere that some machine learning methods have made some progress, but they tend to be developed in different ways by different modeling groups and different researchers. So when we think about how we use these for climate change, it's usually through the biggest coordinated effort is through this UN coordinated set of experiments called the Coupled Model Intercomparison Project, or CMIP. We're at CMIP 6 now, so every few years they do this, and there are large interdisciplinary organizations that develop models, and the UN WRCP, the World Climate Research Program, tells them, run these experiments because we think this is how much carbon will be in the atmosphere in the future. So in Australia, the big modeling center is at CSIRO. They run a model called Access. There are modeling centers in a very large number of countries, and we now have about 49 models all over the world that participate in this activity. Here on the graph, you're seeing output of simulations from those models. And the different colors represent different scenarios that that coordinating body gave them. So the coordinating body says, this is how much carbon dioxide is going to be in the air if we get our act together and pull a lot of carbon out and all switch to green technologies. And that's the green set of lines there. Or maybe we'll go business as usual, and that's like the red set of lines, so it goes much higher, the temperature. But it is important to know that these temperatures aren't the only thing coming out of these models. They're fully resolved spatial and temporal data sets. So here at the top is an example of water vapor moving around in one of these models from one of the models based out of the UK. Now that cloud around the lines is uncertainty, right? And where that uncertainty comes from is those few terms that I was telling you about where modeling centers have to make choices. They're all solving those same 5 equations, but they're making different choices about how to put in those few terms that cannot be resolved. And that is one of the biggest sources of uncertainty here. There's also some uncertainty that arises because you can't perfectly specify initial conditions. And so many modeling centers will run an ensemble with slightly different initial conditions for their models. But the bigger source is really these decisions that people take. Now, what that means for spatial information is that although the models get a lot of things right, they do produce slightly different answers to any question you might ask. So this is an example of an El Nino event that I took from 4 different models produced by 4 different modeling centers. So there's the Australian one, a German one, an American one, and a French one. And this is showing how anomalous the temperatures are in the ocean during that El Nino event. So the spatial pattern is different between all 4 of these. Even though they're all getting this characteristic Pacific warm anomaly along the equator correctly. So this is very impressive. Before I go on to criticize this more, I want to be clear, they're getting a lot right. They're just solving those 5 equations and they were able to do this. There's nothing forcing them to do this. And you get all the major features of the Earth's circulation. So you get the East Australian current, you get blizzards in winter over Canada, you name it. You're really able to get the whole geography of the world from those 5 equations. But you do get these subtle differences, and those differences matter for people who care about their rain and their temperatures. So at the center of what I want to do here there is assess things like which of these is closest to reality, how trustworthy is each of these, and what can we do about the uncertainties that we have. So going back to this east-west gradient that I talked about earlier, this is a source of some controversy in the field because the observations have been showing that over time, the Eastern Pacific is not warming as fast as the Western Pacific, and so that gradient has gotten stronger. So those are the orange dots showing the strength of the gradient, and the time is on the y-axis. The blue diamonds, however, show the CMET models, and they have been consistently predicting that the East Pacific should warm really fast, and that just hasn't happened. So what does that mean then for our predictions of how El Nino is going to change? As of now, it's widely believed that El Nino is going to become more extreme, based both on certain physical theories and on climate modeling. But what does this discrepancy do to our certainty about that prediction? So in order to do that, we are looking into thinking about sea surface temperature data as a distribution and how to characterize it in smart ways that are really relevant to the phenomenon at hand. So these four charts are showing you the mean variance, skewness, and kurtosis. That's the first 4 moments of the sea surface temperatures. So along the x-axis is longitude. This is, so you have the west is on the left and the east is on the right. And over time, you can see that the mean is increasing through the whole basin. So this is the distribution assessed over a sliding window in time. The variance has sort of more of a spatial distinction between east and west. So there's this chunk in the west that has very low variance and higher variance in the east. The skewness and kurtosis shows something quite interesting to us, which is that there is this gradual increase on the right-hand side of the image where in the East Pacific, the skewness and kurtosis are changing. And in the West, it's much more of an irregular pattern. Now, when we looked at this in one of the models, we found that that sort of spatial subtlety is not being captured at all. You can see how different this is. So to dig a little deeper, we wanted to see which features of these are really playing an important role. We're going to use a tool called Quantile Regression. So the basic idea there is that instead of performing a regression to get a mean through your data, you usually fit a line that goes through the mean, right? And instead of doing that, you look deliberately for quantiles that you're interested in. So this will let us look at the various aspects of the distribution that might be changing. So one early result on that, we have a map again, where the left is the west and the right is the east. And on the y-axis here is the quantile. So there's the 20th percentile to the 80th percentile that's marked out. And the colors are showing us the trends in those quantiles. So what are, how are those particular quantiles changing at each point in space? The first thing to note is that the trends are positive everywhere. So, everything is really warming up. That's climate change. But one really distinct observation here is that the West is warming way faster than the East is warming. And that's consistent with that paper that showed the discrepancy. However, in the East, the upper tail of the distribution, so you can see that's about the 90th, 95th percentiles, those are warming really fast at comparable rates to the West. And that's not something you would have picked up if you had just looked at a regression through the mean. Another feature that, that came out of this analysis is that there are basically 3 distinct spatial regimes in the Pacific, where we are used to thinking of 2, like all those schematics I was showing you, we're used to thinking of 2 interacting spatial areas. But what we found was that there are basically 3 different types of change that are occurring. So there's the West Pacific, where there's rapid warming throughout the distribution. The Central Pacific, which is sort of warming more slowly, but still warming throughout the distribution. And the East, where you have this really distinctive behavior in just the upper tail of the distribution, but less warming in the bulk of it. So then we thought to look at the gradients between each possible combination and look at how El Nino activity, so on your y-axis is ENSO activity, and on your x-axis is each possible difference. So there's west minus east, west minus central, and central minus east. And you can see the central minus east has the highest correlation, which was a bit surprising because we typically think of the West Pacific as being sort of one of the governing pieces of that. So to summarize, ENSO comes from coupled feedbacks, and that makes it a very tricky problem. We generally use climate models to forecast climate change. And while they get many things right in an amazing way, they do have some flaws. And one of those is that they haven't quite been able to simulate the trends in the east-west gradient of the tropical Pacific. By doing a quantile regression, we were able to get more detail on what changes have actually happened in the real world. And we found that there were 3 natural spatial regimes where change was happening. And this gives us a new perspective on which aspects of the gradient we might want to explore in the models or improve in the models. So with that, I'll wrap up, and thank you for your time.